Mathematical Induction Part 3. We've already dealt with proving divisibility by mathematical induction, relationships such as greater than or less than with mathematical induction, and in Part 2 we proved the nth term of series and the sum to n terms of series using mathematical induction. This is just a practice video now, where what I'm saying to you is that it's for you to work through, so pause each time and try each step yourself. So now you're going to do mathematical induction and prove that. So now what you do is you pause this and you do the first step yourself. Whatever the first step happens to be, you do it. I'm going to be giving hints along the way, so pause before the hints. Right, so pause now. Try it. Okay, now, first step, n equals 1. For n equals 1, left-hand side just means first term. Right-hand side means substitute 1 into the formula on the right-hand side and hope it comes out as 1. That does become 1. 1 times 2 times 3, 6 over 2, 6 gives you 1. So it's equal to the left-hand side. Now we need to get on to the general rung. So we say, assume true for n equals k. That formula with a k. Now we need to show that we can get on to the next rung from there. So we add the k plus 1th term. Now we go to the rough work. We need to end up with that for k plus 1 on the right hand side. What I want you to note is that this is factorized, so don't take this and simplify. Yes, certainly, find a common denominator, we need that, but don't take this all the way down to just terms without factors, because we need it factorized, so stay that way. There's the common denominator. That over 6 plus 6 times that over 6. Do you notice the common factor? Yes. K plus 1. K plus 1 is a common factor, so we take it out. Notice k plus 1 comes out, so we have k times 2k plus 1 left, and we have 6 times k plus 1 left. Now we're going to simplify that bracket. Now looking at that bracket, is it the same as that? Yippee! Now we're going to look clever, because we're going to go to there, from there to there. And we do our closing touches. True for n equal to 1. Based on the fact true for n equal to k, it is true for n equals k plus 1. Therefore, by mathematical induction, true for all n elements of natural numbers. Another example. Do it yourself. You don't learn maths by watching. For n equals 1. Left hand side 2. Right hand side sub, you get 2 equals left hand side. True for n equals 1. Assume true for n equals k. There's your formula. That's for n, there's for k. Add the k plus 1th term to both sides. Notice once again, that there is still there. That there is still there. All we've done is added the next term onto that side by taking k plus 1 instead of n. A common error is for people to take k plus 1 instead of n there and try to add it in. No, no, no. We're trying to get to there with k plus 1 instead of n on the right-hand side by adding k plus 1 instead of n on both sides. Right, now we need our rough work. We need k plus 1 instead of n. There it is there, which simplifies to that. Looks to me as if we should simplify that down to get a quadratic, because I don't think we'll have a common factor. No, we won't have a common factor, so we need to simplify it down to a quadratic that then factorizes to there. Here we are. That over 2, and this over 2 will become 6 times that minus 2, and it simplifies to 6k plus 4. We've gone from there to there because we knew to go from there to there, so we recognize now we have that. In fact, when we got there, we recognized that it was that. And then we just follow the step back to get there. True for n equals 1. N equals k means n equals k plus 1. True for all by math induction. Here's one involving powers. Left-hand side, first term. Right-hand side, substitute 1 for n. So you get 2 squared, which is 4 minus 2, giving you 2, equals left-hand side. True for n equals 1. Now we need to get on to a rung. Assume true for n equals k. That formula with a k. Now we need to get on to the next rung. Add the k plus 1th term. Once again, that's going to stay. That's going to stay, but we're going to add in the k plus 1th term, k plus 1th term. There's the nth term. The pth term would be 2p. The gth term would be 2g. The 12th term will be 2 to the 12. The k plus 1th term will be 2 to the k plus 1. There we are, 2 to the k plus 1. Notice, that is still there. That is still there. We've added a new term in there and added the same onto that side. Now we need help from rough. What do we need to end up with? That with k plus 1 instead of n. There we are. 2 to the n plus 1, so 2 to the k plus 1 plus 1 minus 2, which is 2 to the k plus 2 minus 2. Now if you have a look at this, you have apples plus apple plus apple. What does apple plus apple give you? I'll take you back to grade 7. Apple plus apple gives you 2 apples. Grade 8, maybe grade 7, when you multiply powers with the same base, you add their exponents. And that's a 2 to the 1. Therefore 2 to the k plus 1 plus that 1. Well look, there we are. True for n equals 1. Based In fact, true for n equal to k, true for n equal to k plus 1. By math induction, true for all n elements of natural numbers. Yo. For n equals 1. Left hand side, first term, which is 1. Right hand side, sub in 1, 1 times 2 is 2, over 2 is 1, squared is 1. Equals left hand side. True for n equals 1. Let's get on to a rung. Assume true for n equals k. That with a k. Now we need to get on to the next rung. Add the k plus 1th term. At the risk of harping, I'm going to say, notice that is still there. Notice that is still there. So we have not got rid of anything, we have not done anything to those terms. But we've added the k plus 1th term, which is k plus 1 cubed, and because we added it there, we added it to there. Now we need help from rough. What do we need to end up with? That with the k plus 1, k plus 1, and instead of multiplying out, I'm going to say, well, k plus 1 is k plus 2. We've got bracket times bracket all over 2, all squared. So therefore, k plus 1 squared, k plus 2 squared, 4. So I'm going to find a common denominator. There it is there. Don't multiply out. We need to end up there, you see, which means there. Yes, you see, you have a k plus 1 squared common factor. Let's take that out. So k plus 1 squared comes out, you're left with a k squared from there, and you're left with the 4 times k plus 1 from there. Simplifies to that, and I'm seeing the light, because there's our k plus 1 squared, and have a look, k plus 2 squared, k squared plus k, 4k plus 4. There we are. Now I have that, so I can go straight to there now. Thank you, Ruff. True for n equals 1. True for n equals k means true for n equals k plus 1. Math induction, true for all n elements of natural numbers. Let's go back to the first part 1 of mathematical induction, just to remind ourselves, slightly different divisibility question. We're now not going to do left hand side, right hand side, remember? We're just going to deal with that, so we're going to say 4n equals 1. And we're going to say that equals 1 times 1 plus 1 times 1 plus 2, which gives us 1 times 2 times 3 is 6. Ah, it is divisible by 6, so true for n equals 1. Assume true for n equals k, which means if I put a k in there, it's divisible by 6. Here we are. That is divisible by 6. Now what we're going to do is take the k plus 1th. We're going to take that with k plus 1 instead of n. For n equals k plus 1, we have that. Now we may not even need rough here. Let's have a look what we end up with. I've simplified to there. Now, I need to try to get that and separate the rest out. Remember, that's what we did. I need to try to get that out of this and separate the rest out, because then that is divisible by 6, and hopefully whatever the rest is separately we can prove divisible by 6, because that is divisible by 6. So we have our k plus 1, we have our k plus 2. We need a k. Well, have a look. K plus 3 times these two brackets gives us k times these two brackets plus 3 times these two brackets. There we are. Notice I've used distributive law of that on k plus 3. So that times k and that times 3. There we are. Have a look what we have here. We have that, we have that. So we can say, well, that is divisible by 6 by the original assumption. Now we have to try to prove this divisible by 6. But this only has a 3. So we need this to be divisible by 2. Do you notice that these are consecutive numbers? And if you take two consecutive numbers, one must be and the other must be even and odd. So here's my reasoning. Since 1 of k plus 2, 1 and k plus 2 must be even, because they're consecutive numbers, 3 times k plus 1 times k plus 2 must be divisible by 3 times 2, which is 6. Therefore, that is divisible by 6, because that is there. That is by this reasoning. Therefore, it is true for n equal 1, based on the fact true for n equal to k, true for n equal to k plus 1, by mathematical induction, true for all n element of natural numbers.